Hello students, let's come to the next exercise. Here, let's have a short look at our exercise, and today we want to simulate NACA, NACA airfoil profile for the wing of an airplane. And the NACA is a profiling system where wings are formulated and different geometries are formulated, and you can have a close look at this picture here. And let's look at the exercise. Later in the following lectures you have to prove that your airplane has high lift forces and low drag forces, and so we want to model a wing, and the wing should be in a surrounding of 20 meters, and the wing should have a length of 10 meters. That is really important that you all take wings with 10 meters length and 600 kilometers per hour velocity of the airplane, because if you change these values you will get, of course, totally different forces. So let's start modeling this model in the design modeler. Here's our workbench, and we want to choose from the toolbox a problem, and we want to choose a fluid flow problem with CFX. We drag the problem on our project schematic, and here you see we have geometry, we have again mesh, we have the full workflow, setup, solution, and results. And the design of this workflow is really convenient inside this, if you stay inside this workflow. Okay, so first take a right click on geometry and don't use space claim, please use the second point, use design modeler. That's very important. Do not double click on geometry, otherwise you will choose space claim, and we want to model with the design modeler today. So let's have a look at our screen. Here's our design screen where we can design the airfoil. And first, before we start designing our geometry, we must decide which plane we want to choose. We have X plane, XY plane, ZX plane, or YZ plane here. And let's go back to our exercise, check it. Yeah, let's say we take XY plane and we use Z plane for the settings of velocities. So here's the XY plane, and take care, now the ruler is a bit big, we have about 30 meters here, so you have to scroll in a bit until you are at 1 meter or 1 meter 50, more or less. And now first step we want to do, we want to start our airfoil geometry. And one thing I want to mention here, if you now start sketching, try not to try to prevent that bunches will be fixed on the axis. This will make your whole design a bit more difficult. So we start with the nose, and we take here this spline in the drawing menu, and you click with a small pencil and the left mouse button here on one position, on the next position, and try not to get fixed on the axis, on the x-axis. Try to click somewhere on this somewhere else. Okay, so, and now make the third click, and now you see this should be your nose. Now don't click with your left mouse, click with your right mouse and choose open end. Though this is the first nose of your wing, and it looks pretty cool. I think this wing nose is not so bad. And now we want to design the next steps. Choose again, stay at spline, choose again the bunch here, click with your left mouse, click somewhere else with your left mouse, and at a third position with your left mouse, and then click open end, and this is the top of your wing. It looks good. Okay, now start to look at the bottom of your wing. Click again on the bunch, click somewhere else, maybe here, click, we make it a bit more complicated, click here somewhere, choose close end. And now we just need here some fins at the end, and we can again choose splines. You can decide it on your own, but it's also more easy. We can also choose a line and a second line. Maybe it looks like this. Okay, you can design the wing if you have other design ideas. Design it in another way, but this wing, it's not a NACA profile, but more or less it will fly somehow. It's a first step. Now we need some additional points, so-called construction points, to change the splines later a bit better. And you can choose here a construction point, maybe here and here. So, and now later on, I think we can start a simulation with this airfoil, but later on we want to modify our airfoil a bit. So please go to the modify toolbox and choose drag. And now try to drag the bunches a bit. Try to drag the points to see if they are draggable, if you can change them. So yeah, good at the back. The tip is not so really convenient like this. Yeah. So it looks good. You can change the splines, you can change the geometry, you can have a lot of freedom by designing your own airfoil. Okay, now before we go on, before we do our mesh, there's one additional thing I want to teach you. I want to teach you how to use the dimensions. Now, I think our airfoil is pretty cool now, and take care that all the splines are closed. If you have any holes here in the wing surrounding, then you probably can't do the model later. So let's go to some dimensions, and here you have horizontal dimensions and vertical dimensions, and now you can choose them. You can choose, for example, here a horizontal dimension, and if you look closely here at the bottom, you see now the dimension is measured. It's 2.7869 meters. And if you now want to change it later on, maybe to 2 meters, just click here and it will be changed automatically. Though this is a pretty cool feature to make an optimization and automatization of this geometry later on. So, and it's a good feature to really get defined points. Yeah? That's important. Not to choose any points. Later on, you have to do some experiments with this NACA foil, and you have to learn something about it. So you should have designed really defined points. For example, just click on the axis. So 1.4. Okay. Or maybe we can choose this point here. Okay. 0.6. So I think now we have a good parameterization. Maybe also this design point here can be changed a bit. Maybe make it a little bit smaller. Okay, I think the first design of your airfoil is finished. You have parameterized all these values. You can change them later on, and you can have a close look. You can have a defined airfoil, and please always try to document your work, to sketch your work. So I want you to choose PowerPoint again for this, and you don't have to use your, let's take maybe this design for PowerPoint. That will look pretty fine. And now you can choose so okay, now we make our screenshot. Yeah, okay, maybe shift it a bit into the direction of the ruler, then you will get also more information about heights, and you see your X, Y axis. That's also a good thing. You can use this, and you make a screenshot. You enter it here into your slides. You can make it a bit smaller, and you can crop it like this. So I think that's a good documentation of what you did. And maybe to show that you did your first serious design, you can also make a screenshot of this table here. Yeah? So that's also a good information. Crop it again, like this, and you can show something. You can tell something about your dimensions and your designs. I think that's interesting information. Okay, and later on, if you do the optimization of the airfoil, if you choose some other lengths or dimensions, you can always tell the audience what you did. Okay, that's a good first step. We can write our text later on. Okay, please always don't forget to save all your results, and let's call it airfoil optimization. Or so that's a good name, and you have your, maybe you choose a title, call it airfoil optimization for company, and you choose your own company name here to tell the audience what you did. Okay, that's some first good slides. I think that's a good layout for our slides. Okay, let's come back to ANSYS Workbench. The first design is nearly finished, but now we have to add an extrude. We have to go back to our modeling. We must add an extrude, and let's look back in the exercise. The given data was for the height of the extrude should be about 10 meters. Make it 10 meters, don't make it shorter or longer, otherwise you will change your forces dramatically. Okay, here something happened, bug or so. I want to delete it again. To go to the sketch, I have to choose it. It should be highlighted in yellow. And now again, add the extrude, go to apply, to choose the right sketch, go to generate, and you see this is your first wing, it's your first airfoil, and it looks pretty cool. I think it will fly. That's also something important. You should learn how to create an airfoil that can fly. Flying means the forces has to go into the right direction, into the plus y direction. If the forces will go into the minus y direction because of your design, the airplane will not fly. Okay, now the extrude is finished, and there's one last step we have to do. We have to define the selections for the airplane. We have to name it airplane or airfoil or NACA profile. Anyhow, so you choose the first plane, and now to choose the second plane you have to press Ctrl on your keyboard, and then you can choose with the mouse the full airfoil. And let us only choose okay, let us choose all the areas. It will not change anything, and it will not make any big changes to our side. Okay, and now if everything is highlighted in green and you choose it by the selection filter of faces, go to right click, choose named selection, go to apply, and look if everything is highlighted in this light blue color, and then press generate button. So your first named selection is now finished. Press on named selection 1, please check if it will be highlighted when you click it with the mouse. And now if you're on named selection, go to right mouse button or press F2 and choose rename, and now we name it airfoil. So that's a nice name. You can also call it wing, you can call it in any name, but please don't use the German word Flügel, because the German signs will not be accepted, and this often causes problems later on. If the students use German letters, the program will crash afterwards. Please prevent this. Okay, this is our airfoil, but it's just the geometry of the wing, and now we want to design the geometry of the air around it. We want to design the space in the air where our airplane flies, and there's a pretty cool feature in the ANSYS Workbench to do this really fast and nearly automatically. Go to the tools and choose an enclosure. Enclosure is to design air enclosures or water enclosures or enclosures of any liquid around a wing. So press enclosure, and now the enclosure can have different geometries. For example, a box. But a box here. It is possible to choose a box for our exercise, but much better is to choose a cylinder. I will tell you later why. Choose a cylinder, and now we have to define in which direction the cylinder, the pipe should go, and we should choose set direction. Here, don't choose automatic, choose set direction, and now go to generate to look if your model works. This looks pretty good. Yeah, you have built a cylinder around the airfoil, and I think the design is pretty good. Maybe this is now time where we can make a short screenshot again for our documentation. Maybe we need it later on. If not, also not a problem. Well, it's better we have the picture. So choose it, place it here, save it again, and keep it in mind to maybe you need it for further explanations. Go back to the design modeler, and now we want to make the enclosure a bit bigger. We want it to take 20 meters of the surrounding air fluid. So you just go to this value cushion radius, and we choose radius, let's say 10 meters radius, means 20 meter diameter. Perfect. And we generate it, and now our cylinder has a size of a radius of 10 meter and a diameter of 20 meter. So now we're nearly finished. Go to generate, sometimes from time to time click generate, and now we have to choose the direction from where our air enters the cylinder. And that's also a little trick. I will come to this later. We will not define any inlet and outlet. We will define an opening. And this opening means it's not defined if the air enters or if the air exits a boundary condition. That's a special, really cool boundary condition. So you choose name selection first. Go to apply, don't click anywhere else. Look if the opening is highlighted in light blue, and go to generate. And check if the small flash is gone and the green tick is already here. And maybe from time to time click on the models to see, click on the airfoil, click on the enclosure, click on the name selection to see if everything is fine. Okay, now we have defined our second name selection. Go with the left click, mouse click on the name selection, press F2 or right mouse button and change the name to opening. And that's from the mathematical point of view. Normally you have to define if you have an inlet or an outlet, but if you choose this opening, it's not really defined. So it can be inlet area or it can be outlet area, and that's a good feature because we really do not know if the airflow will go from where it will enter and where it will exit. We will define it later, but up to now it's not defined. So this enclosure feature is the right feature for this situation. So now again, don't go to save, please. Don't go to export. Don't change anything. Just close the design modeler. Okay, go back to the workbench and check the tick here, the green tick, geometry is finished, and now you should save it. Always save your project from the workbench. Never save it from a single program, otherwise you get lost. And we can choose a name, for example airfoil design number 1, and prevent blanks, prevent German letters, prevent French letters, prevent any special signs even in the path of your model. Okay, and now geometry is here. Go to the meshing tool, choose edit, and it will take some time. You have to wait a bit until the geometry opens in the design in the meshing tool. Yeah, there's a lot of data, and it will be even a bit more when the mesh is finished. Look at the geometry, it looks pretty fine, it looks good. You can choose here the mesh. There's a small flash, it's not finished. Go to the flash button, generate your mesh, and wait a while. And ANSYS has chosen a tetrahedral mesh. That is the right choice. You can also choose other mesh versions like hexahedral mesh or prism layer meshes, but now at the beginning tetrahedral meshes are pretty fine and a good choice to model your airfoil. Okay, and we're finished. You can close the mesher, and that's a small bug in ANSYS. There's no green tick, so you have to go to update again. In the meshing tool, I do not know why, but you always have to do it twice. And imagine it's a lot of data that has to be written on your disk, and you need a lot of memory. So take your time, let the computer work, don't click anywhere else too fast. And now we can go to the setup, open CFX Pre, and look in the setup. Your model is here, perfect. And now I have to explain something. The modeler has done a mesh for the airfoil and a mesh for the surrounding air. So you can probably do also heat transfer calculations or calculations of the fuel inside the ring or wing or any other calculations. So you also have a mesh for the wing. You have two meshes. You have a wet mesh for the wing and you have a mesh for the surrounding air. And maybe you need this to calculate any stresses inside the airfoil or any forces inside the airfoil and compare it with the forces from the air around it. But that's something we don't want to do now. We don't want to use this mesh inside the wing. We only want to use the mesh of the air. So please remember, here in my example, the mesh of the air has the name B65, and it can be a different name if you have another design or if you change a bit on your model. Okay, close this principal 3D regions, go to your analysis to default domain, double click it, and now you see on the top of your basic settings, there's a point location, and both locations are selected here. Go to the button with the 3 dots here to select only the B56. It might be another number in your model, but in my model it's a B65, B56. Okay, go to apply, go to OK, and now something happened. I want to delete this, and now you only have chosen the B56. Everything's fine. If the whole geometry gets highlighted in red color, there's a bug inside. Yeah, so maybe you have to delete some default domains. Okay, but now we only have the air domain here, and we will not need the domain of the wing again. So choose the right fluid, choose one fluid, choose air with 25 degrees centigrade, and go to the fluid models. And now here have a close look at the turbulence models. Turbulence model K epsilon is not the right choice for this problem. Take shear stress transport model because then you can get better resolution of the boundary layers around the airfoil. Go to OK, and it is nearly finished. It looks pretty good, but we have to define the direction of the air, and the air should come from plus X direction here. So we have to insert a boundary, and the boundary we should name it again opening. You can choose any other name, but opening is the right choice. And if you choose opening and you choose a location opening, and then you should go to mass and momentum, flow definition, and options. You also choose opening here. No, you choose Cartesian velocity components. That's the right choice, Cartesian velocity components. And then how high should the velocity in X direction be? It should be here 600 kilometers per hour. So you go to, and I teach you in the lectures where can you define the velocity in X direction. It is the U velocity. So you go here, you type in 600 and not meters per second, take kilometers per hour. That's the right value for an airplane, for normal airplane. It will fly about 600 to 800 kilometers per hour. And let's have a short look here at V and W. Go to this value. Okay, maybe check it again, click again. Here you have U velocity in X direction is 600, and V and W velocity in Y and Z direction should be 0. Okay, that's pretty fine choice. And I think we're finished here. Don't go to save again, just close the program. There is already the tick, and now go to save in the workbench. This will save all the settings from setup, and we can start our solution. Then go to update. We can open. Wait a second. Take some time. We can open the Solver Manager, and now please remember the lectures I gave you. Remember, what are these 4 lines? Green, blue, red means momentum balance in X, Y, Z direction. That's something you should have learned from your lectures. It's the numerical solution of the momentum balance. And the yellow line is the residual of the mass balance for your mesh. So if the mass balance has a low, if there are not big differences in the mass balance, if the residual over all the cells, the mean residual over all the cells is lower than 1.-5, we can say our balance is closed and our momentum balance is fulfilled. That's important. Please have a look, maybe read a bit here in this. Please read a bit here. Please document here all. Normally, if everything is fine, if you have no problem, if if you have no convergence problem, you must not read it, but later if the problems occur, you should have a look here. And all the definitions we did in the GUI, for example here, the boundary conditions we entered in the GUI are written in this source code language here, in this special language for the ANSYS Workbench. And also here are the iterations. Please remember our propeller calculation we did on a sheet of paper. I explained you what the iteration is, and we did several iterations to find right velocities of your propeller, and that's totally the same that is done here. It took about 22 iterations to get the system of equations solved. Okay, please have a look at this file. You will need this knowledge later if the code crashes or if some problem occurs. Close it, and solution is finished. You can go to the results, you can highlight, and you can right mouse button click it, and then you see here your geometry. And that now I have forgotten something. That's not good. I want to close it. I forgot to define where our wing is, and I need this definition. Go back to setup, go to default domain, and that's really a powerful feature in the Workbench. If you realize that you forgot something, you can change it really fast later on. Just go to insert, boundary condition, and I forgot the airfoil. I have to define it, and I want to define it as a wall, and okay, it's a little bit difficult. So I choose all the areas where my airfoil is. Yeah. Check that you only have chosen the cells from the airfoil. Otherwise, you will have wrong force calculations later. Okay, choose a wall. Go to OK. Now you see you have your airfoil, you have your default domain, you have your opening. And if airfoil is a wall, you don't have to define anything. Take a smooth wall, take no slip. That's also something I teach you in the lectures. What is a smooth wall? We will not have any roughness. Okay. Maybe have a short look. That's a new feature. There's this high roughness, the icing. Maybe it's a new model for icing of wings of the airplane. I will check this later. Okay. Go to OK. Go to update solution. Now in this situation, normally I always ask you to delete all the old solutions to clear them, but here nothing really, I didn't make any big differences in the geometry, or I didn't make any great changes in the boundary condition. I just changed the naming definition, so we don't really need a full simulation step yet. And you can go to result, edit, And now we can switch off this surrounding walls and click on the airfoil. And if you now want to change the color or change anything on the airfoil, you can also double click on the airfoil and change it maybe to white. You want a white airplane. And now we want to enter some streamlines. You go to streamlines, you enter them, you have to define the opening and you start them. Okay, now maybe we need some more. This, okay, that looks pretty good. Now we can see how the velocity will be influenced by the airfoil. We have higher velocity on the top of the airfoil, lower velocity on the bottom, and this will cause a good lift force. To visualize it, we go to airfoil again and we change now the details of the airfoil from constant mode to variable mode, and here it is possible to visualize the pressure of the air. You can click on the pressure and we can see at the nose tip we have high pressures, at the top of the wing we have low pressures, and at the bottom of the wing we have pretty high pressures. And that's what now we can, for example, insert also some vectors. We can choose the airfoil. We can choose force here and can visualize our forces. That looks pretty good. So that's how it should look like. We have high forces on the top of the wing. This will pull up our airplane, and we have really small forces on the bottom of the wing. So the airplane will fly into y direction. So I take a screenshot of this nice picture. Maybe change the legend a bit. Change it to fixed. You see, now you can read it much better. I think this is scientific. Okay, you can also go to horizontal design. Go to bottom, center, well, top again. And this is now, I think this is a really nice picture where you explain track forces from the tip of the airfoil and the lifting forces in the low pressure field on the top of the wing. Okay, I take a screenshot, go back to PowerPoint, and maybe I need this text later. And now we can crop it, and we can make some nice pictures. It's maybe not so bad to explain later what we did. Yeah, it's always good to explain what you do. Maybe you can add some information. No. Okay. You can do it in red color. And also try to add an arrow. Make it a bit bigger. And then you get, I think that's a good information. And enter the values. 600 kilometers per hour. I think that's good information about the boundary condition, and you can explain what happened. You can now also the stream trace picture, switch off this one. I enter the stream traces. Okay. Bit bigger, like you can also choose ribbons, or you can choose tubes. You can even choose fishes or anything like this. Okay, this looks pretty nice. Can make a screenshot. You can explain what you did. Can please document what you did. And explain your also something that is always interesting is a mesh, picture of the mesh. Maybe you can add a mesh, and you can maybe add here the first design. Document it a bit. So, okay, I think you got it. You have to do this a bit on your own. Try to document everything in the right way. And before we come, there's one last thing I want to teach you. One last step. Click off the streamlines, and now we want to get real values. It looks nice if you plot any vectors, if you plot any stream traces, but we will need real values, real force calculations, and there's this small calculator tool, the function calculator. Choose a function calculator. You can now choose the airfoil, and for example you can calculate the area here. It's about 120 square meters with a big airplane. Or now go to forces and choose a direction here. Choose the X direction, and there will be a force in X direction. You can copy this. Force on airfoil this was in X direction, and this is a track force. This is a force that is that will rise. This is a force that will increase the fuel consumption of your airplane. If you have a big drag force of your wing, you will need more energy to get higher velocities. And if we are in 600 kilometers, we have a really fat wing, a high force in X direction. We need a lot of fuel, so we call it the drag force. And we need a second force. So the drag force is more or less in the right direction, in the X direction. And now we need the forces in the Y direction, and the forces in the Y direction are the good forces. Yeah, that's your lift force. You can copy it, place it here, and this is a lift force. Okay, I think that's enough help for you now. Now it's your now you have to do some designs, and please, if you do several design steps now to find the right wing, always document your single steps. That's always good if you can show your success, that you can show that you learned something from design to design. It's always good if you present some more designs than one to find the high forces, and always document them. Yeah? Now if you change something here in the geometry in the design modeler, please always document what you did. Do some more designs, maybe 5 or 6 designs to find lower drag forces. Your optimization should be that you get lower drag forces, and your optimization goal should be that you get higher lift forces. So, goal and please always document your work with an Excel sheet. Make an Excel sheet, make a diagram with bars for all the designs to write a conclusion what you did, and you should be able to present this to the audience and to explain your ideas behind the new designs. Okay, I think that's enough help. Let's start your work.